got a nice lineup of talks, not exactly one a week, but something like 2 every 3 weeks throughout the rest of the semester, on various topics. They're all on the web page. And we had a few difficulties in getting someone to speak this week. It's a little bit early in the semester, so I bravely volunteered. So today's speaker got his PhD in 2004 from the University of Manchester. He then went on to do a postdoc at the Arecibo Observatory, and no, he didn't. He went to Bonn before he did that, and then he went to Arecibo Observatory. Then he went back to Manchester, and then has been at WVU since 2006. And today he's going to talk about Extragalactic Radio Bursts. Over to you. Well, thank you. It's a real pleasure to be here. The last time I gave a talk in this building was in the Geology and Geography department, and it's great to be finally in this room speaking to you all about some research that has quite a long story to it, and this story has taken a nice twist this year. So I thought I would take the opportunity to fill you in on that and talk about these extragalactic radio bursts. So what we're talking about primarily are radio flashes. This is an artist's impression showing the Milky Way. This is what you would see if your eyes were sensitive to radio waves. They're very bright flashes of light lasting a few milliseconds in duration. And primarily they've been detected, I'll show you one new example. Primarily they've been detected from the Parkes radio telescope, which is a 64-meter dish in New South Wales, Australia, which is known and loved to many astronomers, and it also got its fame for transmitting the Apollo landings in 1969. So what I'm going to talk to you about today are these discoveries. Tell you just basically what they are as far as we know, give you the facts straight off the bat. I'm going to go rewind back to 2007 when the first one was discovered, talk about what happened in the intervening time, and then what's just happened this year, and then try to synthesize what's known at the moment, give you some possible explanations about what they could be and why they're very exciting as an astronomical source class, and how they might help us understand matter in the universe a bit more, and what we're going to be doing here and elsewhere over the coming years. So being a few milliseconds duration, what they could be is in the realm of relativistic astrophysics, so that's very exciting in itself. This is a picture of a pair of neutron stars, an artist's impression of a pair of neutron stars coalescing due to gravitational radiation. It's possible that the events are electromagnetic emission from such episodes. So let me just start right in with the facts. What are they? So they're radio bursts. They're called fast radio bursts, FRBs for short. They are now named after the year of discovery, month and date, so you can tell instantly when the one was recorded at the telescope. And as you can see, this is a chart showing time on the x-axis, and on the vertical axis it's flux density, which is a radio astronomer's measurement of the power per unit area, per unit bandwidth hitting the telescope. So 1 Jansky, which is our radio astronomer's unit of flux density, is equal to 10 to the minus 26 watts per square meter per hertz. So it's a minuscule amount by our standards. It's a flux of 1 Jansky is what a cell phone would radiate from the moon, something like that.
Duncan, question.
Yeah.
So you have this, or the community has this scheme for the distinguishing. Suppose there's more than one a day.
Oh, then we'll have to rethink.
Okay, so
there are digits at the end.
There are not more than one a day typically, or?
Well, I'll get to that in a second. At the bottom you can see the answer.
Yeah.
But yes, it's a good point. So that's what we're working with for now. So they're very faint radio signals. Radio signals are generally very faint. These are actually bright as far as other radio sources go, so they're quite easy to see in the graph. Flux density time. This particular one has a peak flux of somewhere between 1 and 1.5 Janskys, decays away, and then after a few milliseconds, you're back to seeing the background noise of the telescope. So far, they have been observed at a central frequency of 1.4 gigahertz. That's a favorite for radio astronomers. It's the hydrogen spin flip transition. There's a lot of the basic radio astronomy is done at 21 centimeter wavelength, but we expect these to be detected at other frequencies, but that's where they've been seen so far. A few milliseconds in duration is the width of these pulses. They're singular events, and so each of these 4 bursts I'm showing you here is not from the same source, it's from a different spot in the sky. And they're seen only once. They've been, at least to the limit of our telescope time allowed, we've observed, people have observed these sources for many hours in some cases, or tens of hours in other cases, and seen no repeats. They're seen in different locations over the sky, and I'll talk more about dispersion soon, but they're highly dispersed. And once we understand that, we'll appreciate that these objects are clearly originating from well outside of the Milky Way, our galaxy. So we've only seen a few so far. There's 10 known to date, as far as I'm aware. But based on the amount of the field of view of a telescope and the amount of time that has been spent looking for these objects, we extrapolate, and the authors of this paper, which has just come out, one of which is in the room, have come up with an extrapolated event rate of about once every 10 seconds over the sky.
Duncan,
Yep.
since this is the spin flip, the frequency of the spin flip transition, and radio astronomers have been looking at this for 50 years, why don't they see this all the time?
I think the reason for that is it's a very short time duration, and it's only in the last decade that really pulsar astronomers have been looking at the radio sky with sufficient resolution to see them. Yep. So here's the sky. If I knew how to dim the lights, I would. Just a beautiful image that I got installed from National Geographic, showing about 5,000 square degrees of the sky, about 1/8 of the entire sky, something like that. In the southern hemisphere, you see the band of the Milky Way. There's a comet for good measure, flying off into the distance. This is the large and the small Magellanic Clouds. Those of you who've been to the southern hemisphere will have been amazed by this. And those of you who haven't, I definitely recommend going somewhere in the south that you can see these objects. They're just so beautiful if you go to a dark site like this. So these are our nearest neighboring galaxies from the Milky Way. So we're sitting in this band of stars and gas and dust. And what I was thinking of when I came to WVU 7 years ago was what could I do here that has the minimum amount of telescope time investment. Doesn't require large computing resources because our lab wasn't set up back then. But it's a potentially interesting project, and it's something I can give to a student to have a look at. And so I was intrigued by a survey of the Magellanic Clouds using the Parkes telescope that had uncovered 20 pulsars so far. And that was published right around the time I arrived here. And this is the Parkes, this is a close-up of the Parkes dish, that 64-meter dish I showed you at the beginning. This was a receiver being hoisted up in the late 90s into the focus cabin of the dish. It's got 13 different radio astronomy receivers, 20-centimeter receivers. You can see they're arranged in a hexagonal pattern there. And so it's allowing the telescope to receive electromagnetic radiation from 13 positions in the sky. And so I was aware of this paper that came out where people have used this system to look at the large and small Magellanic Cloud for pulsars, so looking for extragalactic pulsars. Most of the pulsars that we see are in the disk of the Milky Way. But these are well beyond that, and here are some arrows pointing to positions of pulsars. These are contours of emission, 21 centimeter line, ionized hydrogen emission. But just basically outlining the galaxy. This is the footprint of the receiver on the sky. It shows you there's 13 different positions. This is where we found the original burst. I'll come back to that a little bit later on. But I knew that this was an interesting experiment because it had already found a bunch of pulsars in the Magellan clouds. But as I read the paper where they were searching for pulsars, and I won't talk much about pulsars in this talk, but we're familiar that they're rapidly rotating neutron stars, and they function much like a lighthouse where the beam sweeps past our line of sight and we walk along the beach. Pulsar's electromagnetic field rotates as the star rotates, so the pulsar's magnetic axis rotates, and we get this beam of electromagnetic radiation. So we get these pulses of radio emission that are very well studied, and they've been found. And so that I knew that they'd pretty much searched the data for those types of objects. But one thing I noticed that they hadn't looked for is looking for so-called giant pulses. Now this is a very well-known phenomenon, as it turns out, but quite rare, with relatively few examples. This is an optical image showing the Crab supernova remnant, the remains of an explosion that took place over 1,000 years ago. And superposed on here is a radio time series. This is not what we actually see when we look at the crowd, but what the mind's up, the artist's impression, so to speak. And when we look at this particular pulsar in the crab nebula, it occasionally emits giant pulses that are thousands of times greater than the mean. The regular pulses are buried in the noise here, and you see them after you average. But these are very easy to detect. You just set a threshold on your radio data and just look for events above some noise threshold. And I was quite surprised that they hadn't done that. So that was an easy project to do. So I assigned a student the task of doing this. And we had a little bit of data processing to deal with. The main concept that I need to get across here is this concept of dispersion, which is a very common problem for radio astronomers and particularly pulsar observers to deal with. Basically what you've got is the spinning neutron star sending out broadband radio pulses that they don't travel through a vacuum, so they're not traveling at the speed of light. They are actually dispersed in frequency by an ionized plasma in the interstellar medium composed of free electrons and other things. But the free electrons are the main agent here. They have a typical number density n sub e, and those electrons are produced by UV radiation from stars, but so they're floating around the disk of the galaxy. And those of you studying electromagnetic theory are familiar with this cold plasma dispersion law, where the refractive index of a plasma in these sorts of conditions is frequency dependent. You can write down a relationship between the refractive index in terms of basic physical constants and the number density of free electrons in this case. I need an old-fashioned pointer, but maybe I should just use the mouse. This is the refractive index relationship here for this particular case, and the high frequency radio waves travel fastest through the plasma and arrive first at the radio telescope. And you can see that effect here. This is a graph of frequency versus time, and you can see that the two particular pulses from pulsars, as it turns out, Laura gave me this picture, and you can see the pulse dispersed in frequency, that gives that effect. And it's very easy to deal with. Basically what you do is you take this, this array and you just delay the lower frequencies appropriately and then add the signal together. And if you delay by, say, this channel by this amount, bring it back to this reference time here and do the similar thing for the other channels, add them together, you get that those pulse profiles at the in the top panels there. And so this is a well-known phenomenon. We're used to dealing with it, and so we have to basically take the data from this survey and process it as a function of what we call DM, dispersion measure. And dispersion measure is, as you can see in this formula here, it's the integrated column density of electrons along the line of sight. So imagine looking at one of these sources through this plasma, and you're basically adding up the number of free electrons along the line of sight. You're integrating over that number density along a path length dl. If that number density is approximately constant, then you get the simple relationship over here on the right, where d is the distance to the source. So dm is what you measure, the dispersion measure, and you basically get that by measuring this delay here. It's a known quantity. N sub e is something that you can put in as a model for the galaxy in terms of other measurements. You can synthesize other measurements from different sources. There are quite good models now for the free electron content of the galaxy. So you can solve this integral quite readily and find the distance to the source. The little graphic there shows a side-on image of the Milky Way, showing the sun offset from the center of the galaxy. So if you imagine looking at the Milky Way from afar, we would be at that position there marked by the sun. And imagine that black flattened pancake there is essentially following the distribution of free electrons in the galaxy. So as we look at radio sources through different directions, so say we look along here, for instance, the dispersion measure is very, very high. And because we're looking through all of this column of material. But as we look away from the plane and look in this direction, the dispersion measure is quite low. And that's some rather interesting units that only astronomers can come up with. The DM, you can see this. The DM is DM has approximately a value of 30 centimeters per minus cube parsecs for a distance of 1 kiloparsec away. That's the rough scaling relationship. And so if you look along the galactic bulge, you can quickly reach DMs of order thousands in those units. But if you look away from the plane, vertically upwards, the DM contribution from the galaxy is about 20 or 30 units. So that's a very crucial piece of information, because the Magellanic Clouds are not along the galactic plane, they're kind of they're down in this direction. We were looking over here. So we get relatively little dispersion from the galaxy. So we processed the data, and I set the student up with this exercise. And David Narkovic, the student that's the physics undergrad student at the time, was looking at a series of plots like this one, where the main graphic is down the bottom here. We see time along the x-axis and dispersion measure on the vertical axis. And you can see there that there's the different dispersion measures of the different trials that we assume when we process the data. We don't know what the dispersion measure of a source is, so we try lots of different values. And those little dots there are events. Some of them are very low significance. The smaller the symbol, the closer they are to the noise threshold. Basically, the size of the symbol is proportional to the signal to noise of the pulse. So a bigger signal is a brighter pulse. What you will clearly see, I hope, is a sequence of pulses at around DM of 100. This is in the direction of the Magellanic Clouds. So only about 20 of those units are coming from the galaxy. The remaining 80 or so are from either the material in between the Milky Way and Andromeda, and the Large Magellanic Cloud, or the Magellanic Cloud itself. So this excess DM is what really helps us to identify these pulsars. And this was a known pulsar that happened to emit a number of not overwhelmingly giant pulses, but bright enough to be detectable. So I thought he would find a few sources like this. The plots at the top there are just different visualizations of the same data at the bottom. So you see the distribution of signals and noises of each pulse, the number of pulses versus dispersion measure that you search along, the distribution of signals and noise with dispersion measure. Really, the main thing to look at is this bottom panel. So I thought he might find some of those, yes?
Do you have to make an assumption about the time duration of the original pulse when submitted?
No, you're only limited by the time resolution of your data. So you either resolve the pulse, you get enough samples across the pulse, or you don't. Yeah. So in this particular case, we're sampling the signals from the telescope every millisecond. Yeah.
I'm not sure, maybe the question meant you depend on the frequency evolution at the source, the evolution frequency of time of the source intrinsically.
Yes, there is a small effect of that across the bandwidth, but that we're essentially just averaging that out because we're adding the signal across the band. So what we're effectively doing is we're observing at some center frequency across some bandwidth, and we're using this de-dispersion technique to just add all of our frequency information together and produce one time series. And so David came into my office one day with this plot, and well, what you can see is very strikingly this very bright event here between around 1500 seconds after the observation started, had a dispersion measure of about 360, and that's quite high. The rest of the pulsars in the Magellanic Cloud are below or around 200. So it's way beyond that point. And also, if I just skip back very briefly a few slides, this was one of the pointings that happened to be actually well away from the Magellanic Cloud as well. We weren't looking in the center, it's this little square here. We just happened to get this extra pointing for free, the way that they covered the area. So we were essentially looking at a column not really having anything to do with the Magellanic Cloud here. So there was really no contribution to the DM from the Magellanic Cloud, the large Magellanic Cloud, or the small Magellanic Cloud in this case. So we see that great big signal there, and when you visualize it in terms of signal to noise versus dispersion measure, you get a 25 sigma detection. It's very, very significant. This stuff over here is interference that can be seen at very low dispersion measures. But you see very nicely here that there's nothing, this plot's cut off. It can go all the way down to zero, and there's no signal down at zero dispersion measure, which gives us a lot of confidence that this is not a man-made signal. Those have no dispersion attached to it. Let me show you that in another way. When you visualize the data as you might like to do, by simply isolating the event and looking at it in terms of frequency versus time. So there's half a second of data, 500 milliseconds along the x-axis. Highest frequency at the top there, lowest frequency at the bottom. That horizontal band there is a malfunctioning frequency channel that's just being ignored from this analysis. This is a very simple data acquisition system. It's basically digitizing the signal with 1-bit precision. So if it's higher than some value, then it's 1, or if it's lower, then it's 0. That's why it looks like a driving license encryption when you look at the noise over there. And this is actually it may seem quite crude to some of you, but because most of the signal is noise, most of the stuff we collect from the telescope is noise anyway, and the signals are quite weak. 1-bit precision recovers most of the information, and it's very easy to process. So, racing across from top to bottom there is the pulse, that black band of high hits. And those white bands there have been superposed by me onto the plot. That's the expected cold plasma dispersion relationship, separated by 10 milliseconds, I think. So it's a constant width pulse going down, as you would expect from the theoretical relationship. So it matches very well with what we see in other astrophysical sources, for pulsars in particular, where this cold plasma dispersion relation is seen by accuracy. The little inset there is what you get if you collapse down in the vertical direction. You add all of the frequency channels together. That's the pulse that you effectively think of from this particular source. It's about 5 milliseconds wide, and then followed by noise. We looked at this for 90 hours at the Parkes telescope, the same spot. After that, and we saw no significant further events. So we seem to have gotten very lucky here and seen this one bright, highly dispersed event. And we had a lot of fun writing this little paper together with David and some other collaborators. And basically putting this out as a very unusual new source, a single event that appeared to be potentially something signposting an entirely new population of astrophysical objects. Because of this high dispersion, we couldn't relate it to the Milky Way, and we come up with some models for the amount of material in intergalactic space, and we estimated back then that it was about a gigaparsec distant. So the Milky Way is about 25 or 30 kiloparsecs across. So much, much further than the scale of the Milky Way, way into the cosmological realm of the universe. And so we posited that they could serve as cosmological probes. But that's all we had. We couldn't localize the position of the source very well because the telescope's field of view didn't allow us to get it better than a few arc minutes. And that's not enough to pinpoint it to a source like a known galaxy or something. And so we took it as far as we could at that point. Some very interesting questions, and some of them we discussed, is why is this source so bright, this initial one that we saw? Why aren't there any weaker events that you might expect from a population? But the implication was that these objects should be detectable in other surveys that have been going on. This is not the only survey that we could look at. So people started then looking at these sources, and what happened next was very interesting. A paper published a couple of years ago now by Sarah Burke-Spalera and collaborators started looking for these events in other data sets, and they found them, and I'll show you later that they're not quite the same, but they were alarmingly, they had a very similar delay to, it's been mentioned, it's been shown there as the Lorimer burst, and that arrow is pointing to the original delay that we saw through the frequency band. So they saw these events, and it was very, very disturbing to many of us why they should have the same delay, because these events, as I'll show you in a minute, are really quite different. They're much more what you expect from terrestrial interference. So they dubbed these events as peritons, after this mythical Greek beast that is a winged elk but casts a human shadow. So it's something that's masquerading as something else. Let me show you a bit more what I mean. Here's an example of some of the peritons that they found. In the top left there is a montage of one particular event in all of the 13 beams of the Parkes telescope. So one thing you notice there, that the event is seen in every single beam. Whereas for our event, it was only seen in three beams off to the bottom right of the cluster. So whatever this is, it's coming sort of into the bore site of the instrument, and it's saturating the instrument for a short period of time. If you look at the frequency structure, it does follow approximately the cold plasma dispersion law, but if you look at that one on the top right, for instance, you see this sort of blotchy nature. The pulse is not broad band. It's not marching across the frequency space with any uniformity. And so that was quite different to the original event. If you remember, it was very uniform. But this was cause for quite concern. We couldn't rule out the original event, but this was the fact that these objects were being seen in all beams with a similar sort of dispersion delay made a number of people quite suspicious and caused me to lose quite a bit of sleep. And it got so bad that even my own wife began to doubt me. She published a paper about a year or two ago. They were looking for these events in another survey. I won't make you read the whole abstract here. The last sentence is a bit depressing. So they said they really should have found these events, and they didn't find them, and so they were questioning whether it really was a cosmological source population. I remained silent for most of this time because I was convinced that of the validity of the signal looking so much different in the dispersion-sweep relationship, but I couldn't explain the fact that no other sources had been seen. So my mother once told me that the best thing, if in doubt, say nout, which roughly translated means say nothing if you don't want to incriminate yourself and you don't really have anything else to offer. But then, right out of the blue came another event that really recharged this whole field. Evan Keane and collaborators looked through the same data set, in fact, as that previous paper I showed you, and they did find this faint event, which has many of the characteristics of the original one, with a different delay, so a different dispersion measure, only seen in one beam, and so quite unlike any of these paradigms. And then this year, the paper that has just come out, and Lena's one of the co-authors on this one in Science, from a new survey with the Parkes telescope with much higher time and frequency resolution, looking at the sky for these events, has confirmed them now as a population. It's found four more that were announced in this paper. Colloquially, they're known as Lorimer bursts. Some people call them sparkers. You might be tempted to abbreviate them to be fast radio transients, but that's probably not a good idea. Fast radio bursts is the technical term, as I mentioned, FRBs. This little graph here is quite nice. It's showing you the distribution of dispersion measure versus galactic latitude, the angle away from the galactic plane. So the red envelope there are all the known pulsars in the Milky Way. So that envelope is effectively matched, showing the electron content of the Milky Way. The four blue triangles there are the new FRBs that Thornton et al. Announced. You can see they have very high latitudes but very high dispersion. So again, inconsistent with the dispersion from the Milky Way. The original event from 2007 is that one there, and that's the one I just showed you on the previous slide, which just again is offset from the pulsar population. So clearly this is something different, and there have now been three other detections I've heard of from Parkes, and one more which I'll show you in a few moments. So they're new sources, and I think it's a very exciting time. If you're a pulsar astronomer, like me, you've grown up looking at sources in the Milky Way, you're not used to studying cosmology, so we have to take a small cosmology class to understand things a little bit further. And I had to remind myself about this as well. We talk about the redshift of sources in an expanding universe. So at the top there, you've got a galaxy, and it's the photon traveling from right to left is basically following the expansion of space, and its wavelength has been redshifted to the red sine wave there. You can see lambda now as it arrives at us on the left there, the Milky Way. It's been redshifted with respect to what happened when it was emitted. The universe was much younger when it emitted, and the universe hadn't expanded enough as much, and so it was a much shorter wavelength pulse when it was emitted. Now we see this longer wavelength pulse that we observe. The relationship between lambda now and lambda emit is the size of the size scale in the two cases. And astronomers write out this relationship here. They define the redshift Z as the observed wavelength minus the emitted wavelength divided by the emitted wavelength. So astronomers do this very frequently. They know the emitted wavelength through spectral line studies. They see a very well-known physical transition like the hydrogen frequency or optical frequencies in optical astronomy. They see spectral lines. They measure their observed wavelength, and then they infer a redshift from that. We often talk about 1 plus Z is the ratio of the observed to emitted wavelength. But a very interesting question then is can we calculate the redshifts of these sources and therefore estimate their distances? Well, it turns out you can. And here's how you do it. At the top here we see the band delay, and so that's the amount of the sweep in time of the pulse across the observing band for one of these FRBs. And so it has a delay of about 4.4 seconds across the whole band. So just so that we're on the same page here. Frequency versus time. Here's the pulse being delayed by the Cole-Plasma relationship. This is what I'm calling the band delay. It's that time there. Okay? So that's what you measure for these pulses. You can measure that unequivocally. And then these other curves over here are different contributions to that delay. So, let's start with the first one. This dotted line here, which is constant with redshift, is the contribution from the Milky Way. It's the electrons in the Milky Way that are causing that. So it's a small fraction of a second, and it is independent of redshift because it's here. This decreasing dashed line is the contribution from the host galaxy. So the host galaxy, let's say where the source is coming from, has free electrons in it as well. The signal had to travel through those to get to us. Notice that delay decreases with redshift, and that's because as you put the source further and further back in space, the band frequency that it was actually emitted at goes to higher and higher frequencies. So we see something at 1.4 gigahertz, but the actual frequency might have been at 2 or 3 gigahertz. And there, the dispersion delay is much less. So that's the origin of that slow curve. This diagonal dotted and dashed line is the contribution from the intergalactic medium. So the electrons, the free electrons that are in between galaxies. There are only models for this right now, based on other measurements. But there's some reason to believe that it's going to follow something like this relationship. The solid line is the sum of those three bottom curves. So what you do is you look for the intersection between the solid line and the vertical dashed line. What you've actually observed is the contribution of these three effects, and then you read off the redshift from that. So the redshift in this particular case is right around here, east. Yeah.
The cosmological redshift is independent of frequency, so I don't understand how it does anything other than shift your frequency versus time.
Yeah, so we're equating something on the vertical axis, which is what we measure, to something that's functioning as a distance estimate. So yes, what we see here is emission at 1.4 gigahertz, but the only cosmological effect is the is where you believe the emission actually came from at the source. So the higher you go out in redshift, because the frequencies are getting more and more redshifted, that's the only cosmological effect here. So what you can see, I hope, is that the delay is dominated by the intergalactic medium. So if we can measure these sources, more and more of these sources, and identify the host galaxies, that hasn't been done so far, because we don't know the position well enough. If we can identify the host galaxies, we can get an independent measurement of the redshift, and therefore calibrate that diagonal line. So right now that diagonal line is basically a model based upon other measurements, but no direct measurements. So this is the first way, this will be the first way of measuring the electron content in space. So let me finish off with a few slides suggesting what they could be. There are 10 objects known to me right now, probably a few more are being discovered as we speak. What could they be? Well, if you do this exercise and work out the distance to the various sources, the rough estimates that we can make right now, you find that they're emitting something like 10 to the 32 joules of energy that we're seeing. So it's a very energetic event. The sun is emitting 2 times 10 to the 26 watts of energy in the optical band. So it's a very luminous event, but it's not as luminous as a supernova, which would be 10 to the 43 or 10 to the 44 joules. So it's high, but not ridiculously so. So it actually turns out that there's quite a lot of sources that could explain that. The other constraint that you have is it's a very short duration, so they must be coming from compact objects where the light travel time across the source is less than a few milliseconds. So, for instance, a neutron star collapse to a black hole is one possibility. We know that this can happen. We see neutron stars accreting material in our Milky Way, and so it's a reasonable extrapolation to say that that's going on. That's rather common in cosmological sense in many different galaxies. Another more speculative idea is the evaporation of a black hole due to Hawking radiation. So mini black holes that around the size of the Earth were deposits to were formed in the very early universe should be evaporating due to the Hawking process. Now, if there's an electromagnetic energy signature that can be detected from those, it's consistent with the time scale of these sources. But I think it's probably I think with all of these source options, you really need to identify counterparts at other wave bands. We want to see associated X-ray emission, see a host galaxy if there is one, and things like that. Because all of these events, they're consistent with what we see, but we can't. They're currently all on an equal footing, and there are more theories that you could come up with. So we need to make progress here, and one of the ways is to look for counterparts to the wavelengths. And so most immediately in the electromagnetic spectrum, but possibly also through gravitational wave emission, we might be able to associate these events with other phenomena. Let's say we can do that. Let's say we can find a host galaxy and measure the distance to that. If we do that, then we constrain the energy budget. We know the luminosity, how much energy was released from the source, right? And that will help us narrow down those previous options that I listed on the slide. As I've alluded to already, the dominant factor in the delay is from intergalactic dispersion. So if we can measure the distance to the source independently, then we can basically calibrate that diagonal line, and in effect measure. We have a probe of the free electrons along arbitrary lines of sight through the universe. So we astronomers have been investigating so-called dark matter and dark energy for many years. This gives us a way to look at baryonic matter, essentially electrons that are invisible through many other means. And so it gives us a new probe of baryonic material in intergalactic space. There's also the possibility of looking at the Faraday rotation of the signal. In our galaxy, we see Faraday rotation of the radio waves due to the galaxy's magnetic field. If there's a significant magnetic field in the universe at large, we could potentially constrain that. That's something that hasn't been done so far. The population of these sources, whatever they are, because they're cosmological, you're looking at such a large range of timescales in the universe, you're going to be seeing different formation rates and different processes as galaxies evolve and at various different times in the universe. It might be more efficient to produce these sources. So as we get more and more of them, we'll start to probe this population of different versions. But what we really need to do right now is to just find lots more of them and locate them in close to real time. Most of the detections I showed you were taken in data taken 5 or even 10 years before the discovery was made. So, it's a long time, it's a long lag time from when they arrived at the telescope to when the astronomer noticed them. What a number of groups are now doing is implementing real-time detection systems that can be triggered by these events as they come in within a few seconds or minutes of their arrival. And that, I think, will be a real game changer, because it allows other astronomers to look with different telescopes at other wavebands. Now, another thing that we need to do is to find these bursts with other telescopes. So far, the Parkes telescope is the only one to find them. And that's caused a number of people to still be skeptical of this. Why they just being seen at Parkes. I think it's really mostly due to the fact that Parkes has observed the sky for the longest in this node. But here's a result that's being put together by Laura Spittler et al. Based on Arecibo data. So this is a different telescope, and we're now seeing another of these dispersed events with an entirely different observing system. So it's my hope that these will become more common with time. And to look at them at different frequencies. With pulsar signals, we're very familiar with the idea of scattering. We have a very sharp emitted pulse that sends away from the pulsar, passes through this turbulent medium in the galaxy, and arrives over here at the observer as basically an exponentially involved pulse with all of these different arrival times and the different path lengths of the scattered rays. That's happening as well in these bursts. Here's the very nice example from the recent discovery paper showing the frequency evolution of the burst profile. So you see at the highest frequency at the top there, it's got a relatively narrow pulse, but it's getting more and more exponentially broadened by the scattering process. So we're clearly detecting scattering in the intergalactic medium, and that's an entirely new phenomenon as well. Final couple of slides. What to do next? Well, we've got different telescopes, different frequencies. It's time to characterize the population. We're starting to do that. I've made a career for myself in working with populations of 1 or 2 pulsars and extrapolating to the whole population. So it's never too early to do that here. There's 10 of them even, so it's good. There's double figures already. Here's a paper that we just put out with one particular source model that shows how the flux density would evolve with redshift. I'm not going to go into this with great detail, but you can basically see with a rather simple cosmological model that you get a prediction for the flux density with redshift that can still be tested. Those two other curves are at different observing frequencies. The source will have an event rate that is a function of redshift as well, and that the curves on the right there show predictions that we use based on the current constraints. But it's just a starting point, and I expect there will be a lot of publications coming out in the coming weeks and months. What's going on here at WVU? Well, people are searching archival data. There's still plenty of that to be searched. So Akshaya is leading an effort here to look at some more ARCS data and hopefully pick up a few more of these. And Natasha McMahon is helping out with that. We're actively looking at real-time detectors at the GBT in Arecibo to really accelerate the progress in this area. So over the next year, that's one of the things that we want to do. And then finally, we're sort of trying to think as big as we can, and actually put some sort of new radio telescope array at Greenbank that's dedicated to look at these. This picture is an old black and white image of the three decommissioned radio telescopes. These are 85-foot telescopes that we use as an interferometer. But there's a lot of real estate there that is in a radio quiet environment and can be used to build a low-cost antenna that's optimized to find these bursts, because they are in radio astronomy terms relatively bright. So we're actively looking at that area, and many other groups elsewhere will do as well. So I think over the next 5 years you're going to see quite a change in emphasis here. These sources are definitely not a fluke. They're very hard to detect, so we still have small numbers, but I think we're going to learn a lot about them in the coming years. That's probably a good point to stop. Thank you very much. So we've got time for a few questions. Yep.
How do you feel like the distances involved? But I'd expect something emitted distantly from even a small solid angle. So by the time it gets here, it can be very spread out. So why is it only detected on one of these detectors on the CDB telescope ditch here?
Oh,
The degree of collimation, essentially.
yeah, it's when you work out even from an isotropically emitting source at the distant spaces, whether it be through the galaxy or much further out, when you look at the angles involved, there's a very steep cutoff in the telescope's response as a function of angular velocity. And so really, the source still appears as a point-like in the sky, just like an optical star would do. So it really is a point-like object. You're not just seeing this. There is some very diffuse radiation. It's orders of magnitude below. Yeah, go ahead.
It's probably a misunderstanding on my part, but if you go back to your 2007 data,
Yeah.
how does a higher dispersion measure translate to a signal of one of these bursts?
Okay. So it's basically a budget on the dispersion measure. So you say, well, you're looking out away from the disk of the galaxy. You measure the dispersion delay, and you get some value. In this case, it's 360 minutes. The models of the galaxy in that direction give you only 25 minutes. If the source was slap bang in the middle of the Magellanic Cloud, you could plausibly associate it with the Magellanic Cloud, because there are enough electrons in there to give you the remaining delay. But it's the fact that it's offset from the Magellanic Clouds that caused us to infer that it's much more distant. But the issue that we had was that our estimate of distance was rather uncertain because of the uncertain nature of the electron content in intergalactic space. So that's something we had to address with its counterparts. Lauren?
Yeah, a quick question. I may have misheard, but your original observation was detected in 3 beams?
Yes.
Is that right?
Yeah.
So it was not exactly a point source.
No, so that would, I can see why you might infer that. The thing that we've got to remember here is that these radio telescopes are rather blunt instruments. So they have actually if you look at the response of the telescope as a function of angle, it sort of falls off with like a sigma squared function. It has these significant power in the side lobes. And so this little square there in that central beam, that's where it was detected brightest. But you notice it wasn't detected in the beam just to the left of that, but it was detected in the beams to the right.
I see.
So it's basically consistent with the position between those two. Even with that information, you can't localize the position well enough to identify a counterpart. Part of the problem is it actually saturates and digitizes in that square beam there. We're not exactly sure what the signal to noise really was.
What is the number of the error in square?
Oh, it's the uncertainty in the position. It's about 4 or 5 arc minutes, which is thousands of galaxies, hundreds of these. Yeah.
From your graphs, it looks like the band delay is defined by arbitrary detector cutoffs. Is that, do you have data where you can actually see where the signal stops in time?
Yeah, the band delay is defined by what the observing band is set to, but that is, the implication is that the cold plasma dispersion law carries on beyond that. It's not when you make measurements at other frequencies at other radio sources, it indeed follows that law. So even though we've got a relatively arbitrary band, the fact that we see it following that relationship gives us a lot of confidence that it's not a function of where we cut the band up.
So when you search for these burst signals, what is your upper limit of the dispersion band?
Good question. Yeah, so initially, if we go back to here, this plot here this is our initial search. You can see the upper limit was about almost 500. So my rationale back then was, okay, there's 20 units from the galaxy, there's maybe 300 units from the Magellanic Clouds, and let's think of the number you first thought of and multiply it by 70%, and just to allow for uncertainty. And so that led us to that number. But in fact, these sources are so bright that you can see them out to much higher dispersion measures. So this initial search cut off at 500. We've since gone back and we've reprocessed up to 2,000. The current searches are going up to 10,000 units.
So that's already in the real-time detectors in green.
That's what people are starting to move towards. To do it in real time requires GPU processing power, but it's becoming available now. It's possible.
The first time you showed the plasma bands,
Yeah.
you were talking about how they were had an equal width across.
Right.
But the picture you showed didn't look like it was exactly equal.
Yes. I didn't talk about. I know.
From that?
Yes, you can. I didn't talk about that. So the white bands are just to guide the eye, and they definitely have the separation is always the same. You can see, I hope, that if you look at the pulse at the top of the band, compare it to the bottom, the pulse itself is broader. It starts to fill the envelope, whereas at the top it's truncated. That is related to the scattering effect that I talked about at the end. So the scattering is a frequency-dependent phenomenon. So what we're probably seeing here is slight broadening of the pulse due to lower frequencies as you probe the scales of the scattering screen. So this is, we believe, an astrophysical effect.
The original source, collapsing black holes or whatever, doesn't care at all about hyperfine transitions. So what you're seeing I mean, the original source is hitting hydrogen somewhere, triggering these transitions, and you're seeing the result of that. But
Now, I think what we're seeing is we just imagine it sending out a broadband electromagnetic pulse, and sources at different redshifts. We see, let's say, 1400 megahertz. At a certain redshift, we're going at, we look at redshift of
you think
1.
the 1400 megahertz is coming directly from the source?
Yeah. So what you're seeing is a redshifted version of, say, 2.8 gigahertz, or whatever it's coming from.
So then you should see this at 2000 megahertz or half a megahertz or something else.
Potentially, yes. The scattering effect starts to become more important at lower frequencies. It should make it clear that this is nothing to do with the hydrogen line here. We're just looking at the electromagnetic radiation in this band. So it's no interaction with. Yeah.
Why do you look at this band specifically? Is it just because there exists data?
It's because the interstellar hydrogen is just so ubiquitous, and when it was detected in the 50s, that was the thing to do, and it still is. I mean, DJ still makes his bread and butter looking at hydrogen from extragalactic sources. And so it's that band that's just still so valuable. So we as pulsar astronomers, we just say, well, we'll just take whichever band you give us, and that just happens to be it.
So all of these bursts have been seen in archival data, correct? Stuff that you've looked at.
Right, the ones, the 7 that are published, that's right.
How many different, I'm assuming they're all coming from surgeons, right? Maybe you're just scanning the sky. How many different surveys have these objects been seen in?
Three at Parks and now 1 at Harrison.
Okay.
So that's 30.
4 different surgeons.
Yeah.
I have a new name suggestion.
Oh, yes.
So you're familiar with Princess Bride and rodents of unusual size?
I think boys know.
I think you need to,
Okay, I need to watch it.
come up with a name similar for this.
Okay. Thingy? Yeah.
So I know it's crucial for this research to have multi-band bands, but it is quite difficult because we know that radio signals comes the latest to Earth. So it's hard to monitor a particular position.
Yeah.
So how do you think?
Right. So if you go to the analog of this, the closest analog is the gamma ray bursts. And so there we saw radio afterglows from the gamma ray bursts, and also associated optical afterglows as well. And that was quite surprising. It was several days of emission where you saw the optical brightness decay. So in that case, the gamma rays arrived first, but we didn't really have time to trigger the telescopes to catch the same event, and we were looking at the afterglow. I think that's what it's going to happen. Same thing here. If there is a emission that's associated with, let's say, it's ionizing a region of gas around the source, then there's going to be associated brightening with that as the blast wave propagates out. Well, if there are no further questions, let's thank the speaker again.